Dr. Fouad Jabber is a professional engineer and a professor in integrated water resources management extension specialist with Texas A&M AgriLife in Dallas. He holds a PhD in agricultural and biological engineering from Purdue University and has researched green stormwater infrastructure, nature-based system, and stream restoration and non-point source pollution management. So he will be talking today about geomorphological forces shaping our riparian habitats. So I will stop sharing now and give it over to Dr. Jabber.
Very good. Thank you very much. Thank you for having me. And this was a great presentation. I actually, he ended with a great segue to my presentation about pollution and sediments. So let's start. So we heard about the function of the riparian area, but what is the function of the river or the stream? What is the main function? If you think hydrologically, a river function is specifically to transport water, right? It's a very important part of the hydrologic cycle. When it rains, there's runoff that comes on the side of hills and eventually gathers in low areas. When there's enough water, it starts creating a channel for itself, and that takes the water fast enough to back to the sea or the estuaries. But another function of rivers that's commonly not looked at is actually the transport of sediment. Sediment movement is as important as the water movement, and rivers have a great function in moving these sediments from upstream areas down to downstream areas. This is actually how beaches forms and riparian areas get enough nutrients and build up as a result. The important thing here is to know that the balance between water and sediment is very important for a healthy stream. And when you have a healthy stream, that function where there's water and sediments that result in a healthy riparian area, you have a healthy habitat for aquatic organisms. You have a healthy riparian area with trees, shrubs, and grasses that grow on the side of the streams, and first they provide food for terrestrial and aquatic animals, but also this vegetation sometimes shades the streams and provide perfect habitat conditions for different vertebrates and invertebrates in the channel. Now, in order for that to work, the channel, as it forms itself, there are features that occur in every healthy stream. These are called pools, riffles, glides, and runs. And these actually are very important also as part of habitat because they allow for the survival of various species in calmer waters, faster water, and the various food that settle in these different systems. So with that in mind, if we keep in mind that this is what makes a river functional and healthy, then if a river is not healthy and needs to be restored, we need to always look at an approach that takes natural design into account in order to fulfill the top 4 functions. And that's been lacking a lot in a lot of the project in the US and in the world, really. So we talked about this balance between water and sediments. Basically, a certain concentration or amount of sediments in the river is natural, and every river have a different amount in it that relates to the flow rate, how fast is the water going, and the vegetation, of course, where is that stream located? If it's on the East Coast, where it's lush and green, you'll have much less sediment that are going into the water. While if it's in a desertic area, even though there's stability and there are vegetation, then you would expect maybe a higher amount of sediments in the water. But these are natural. But at some point, that natural stream have a balance between the water flow in it, the base flow and the storm flows, and the sediment load or concentration in that water. And instability happens when something messes with that balance. So for example, when we start building on the watershed of the stream, we're converting that uh, pervious area where water used to infiltrate into impervious area, and suddenly a larger amount of water comes from typical storms. So when the 1-inch storm used to get I don't know, 1,000 cubic feet per second flow in a large stream. Now, when we start building and changing that watershed, we're going to get 5,000, 6,000 cubic feet per second. And so as a result, you've messed up, you've increased the water flow. So that part's going to become heavier, and that arrow is going to point to degradation. The fast flow with a lack of sediments in it is going to produce very fast flow that produces very strong forces on the banks, and it causes degradation, which is also known as erosion. So you would have erosion, widening, and deepening of the stream. On the opposite part, if, for example, there's a construction site near a stream, and the developer, the contractor, put a large dug up a hole, put a large little sand or soil mountain, and did not protect it with silt fences and other required protection. When it rains, a large amount of sediment is going to go into that stream, but the water amount hasn't changed. It's typical. So what you're having is the sediment part of the balance becoming heavier. And so that arrow is going to point to aggradation, which is the opposite of degradation, which basically means that there's too much sediment in the water. The flow is not strong enough to carry these sediments down the stream as it's supposed to, all the way back to the sea. And so these sediments will start settling, and what you have is little islands building in the stream, or point bars forming at a faster rate than normal. And all these are going to mess up with the habitat, with the function of the stream. And if they continue, they become even, it can become very severe, which is what we actually have in every single urban stream in the US, and specifically in Texas, in Dallas, in Houston, in Austin. You drive, you look from the bridge to the river stream, and you see small versions of the Grand Canyon. You never see this nice, healthy channel with a floodplain and good vegetation on its sides, because of the increased flow in most cases, but also in some cases due to the increased sediment loads that we're allowing to go into our streams. So what is a stable stream? How do you identify a stream that is stable? You have to look at three things when you're looking for a stable stream. You look at the cross section of the stream. You look at the pattern of the stream, meaning you look like it's like a plain view of the stream. And then you want to look at the profile of the stream. Look at how the bed of the stream varies as you go downstream in a stream. So these are the three things that define a channel, and from those you can tell if you have a stable channel or not. The first thing is the cross section. Regular stream, normal stream, how do they form? When you start having rain, let's say you had a straight plane right here, and the first ever rain that ever happened on Earth starts falling on this watershed. Water will start coming down from these hills and starts gathering in the low point. At some point, you will have what we call a channel forming discharge. That is a flow rate strong enough to create a channel for itself. And so that channel forming discharge is going to shape the shape of the channel. After that, as you get more rainfall and stronger rainfall than that channel forming discharge, the forces become so strong that they start creating a floodplain to slow down the flow. So you would start creating a floodplain. They did an analysis on thousands and thousands and thousands of streams in the world, and they found out that the channel forming discharge, which is the flow that allows the water to get to that level in that channel, is always between the 1.2 and the 1.5 year storm. What does that mean? It's the storm that has a statistical chance to happen once every 1.2 to 1.5 years. And so Why is that? It's because it's strong enough that that flow from the 1.2 to 1.5 year storm is strong enough to create a channel, but it's not strong enough to cause erosion above. The stronger storms will cause erosion. If this was, it started forming the channel, and then little by little, when you get the 10-year storm, the 100-year storm, these flow so strong that they're going to erode and they're going to create that floodplain, which eventually ends up being the riparian zone that was talked about in the previous storm. So that's how you recognize a stable cross section. If you go to your cross section, you measure the channel part of your stream and you identify that as the bankful stage. You can look at the hydrology and see, does that channel carry the 1.2 to 1.5 year storm? Does that channel has a healthy flat area at the bankful, which is the floodplain that is well vegetated? If yes, then you have a stable cross section. The other thing you want to look at is the pattern. The pattern means, how does that stream meander? And a meandering stream, a stream naturally meanders because as it goes, the eddies are created, especially if the slope of the land is very high, very strong. It causes these eddies that starts turning, and it starts moving the channel both ways on the outer bands. And as it moves it, what's happening is your it slows down your slope, right? If the slope was 10% right here, but by having a meander, the water have to travel a longer distance to actually still go from elevation A to elevation B. And as a result, it slowed down the slope, and that water slows down. So rivers, as they're forming and as their watershed change, they change curvatures until the slope is slow enough to stop moving the stream. And that's why a channel with a correct meander for it will be stable. And so in order to identify what is a stable meander, we have these engineering terms for a meander geometry. And basically, if we know what's a stable meander for a stream is by looking upstream or for similar streams in an area, we can go back to a bad stream and re-meander it so that it has the correct meander based on these geometrical measures that we take right here. Uh, the amount of meandering a stream does is called the stream sinuosity, and it's usually you divide the distance between A and B along the channel by the straight line between A and B. The higher that sinuosity is, then the more meandering the stream is. The third thing we want to look at is the profile, and so that's going in the bed along the stream, and we want to look for features. And so what it is a sequence of pools and riffles. Pools are these deeper cross section. In most cases, they're on the top of meander bands, and they're deeper toward the outside of the meander band. But when you're walking along the stream, you notice that the water is more or less calm at these points. Water doesn't look like it's flowing very fast. And in reality, because it's deeper, water is coming down, it's slowing down. A lot of these fine sediments, they settle at the bottom of the pool. And that's why it provides food for certain type of aquatic or terrestrial animals. And while the riffles usually are straight sections where water flows very fast, and because water is flowing fast, the only things that settle in these riffles are usually large rocks. And so you can identify a riffle from a pool also from the sediments in the bed. Between these sections, from a pool to a riffle, you have a section that's going a little bit faster, and it's called usually a glide. It's increasing speed as it gets to the riffle. And between the riffle and the pool, you have a run, and that's water that's going fast and slowing down before it gets to the pool. So having these three features, a correct cross section that has a bankful section with floodplain, a good meandering stream that have very well defined meanders, and in the profile having a sequence of pools and riffles. That's what's make a stable channel, and that's what we aim at recreating when we try to restore a channel. So basically, what's the goal of a channel restoration? Restoration should result in the adequate water and sediment balance that will not cause any degradation, erosion, or aggradation, accumulation of soil in the middle of the stream. It improves habitat and promotes diversity, and it promotes riparian vegetation. Now, one question, like I've been giving workshops, day long and 3-day long workshop on stream restoration, and always telling people that if you stabilize the stream, the animals will come back. While it's been always assumed by USDA, by the Forest Service, that this is correct, there isn't a lot of research that went and investigated that exactly. Why? It's because restoring channels using geomorphological concepts like the one we talked about, the cross section, the pattern, and the features, the profile, is a very costly process. No one is gonna do it to see if it restores habitat or not. But luckily, some good faculty in around the U.S., in Virginia, in North Carolina, started doing research when these processes started becoming more common. And so once they knew there's a natural channel design restoration happening, they went and started measuring and collecting data. And all the research suggests that you don't have to go and do an extensive habitat assessment to do this. There was very close relationships between restored channels that used geomorphological approaches and increase in habitat. So they did this research for us. So we know if we bring back the stream to a stable form using natural channel design, it will improve habitat. Uh, there's also they also compared different channels. Channels classify in different forms. There are different types of channels. There's A, B, C, D, E, and F, and G. And they were able to prove that these geomorphologically different streams are actually have a different statistical population of different, depending on what they looked at. Some people looked at fish, people looked at mussel, some people looked at different things. There's also a lot of evidence that shows that when sediments increases in streams due to human interference, construction of bridges, increased maybe a reduced protection of during construction site in the watershed. When the sediment load increased in these streams, the mussel population was reduced. In some cases, they died. In others, they were not able to reproduce as efficiently. And so there is a problem with increasing sediments in water. Also, increased water flows prevented mussel population from attaching to the banks, and as a result, surviving in these areas. So let's go back and look at what can cause instability, right? And so here we have a stream that, as I said, it looks like a canyon. This is when you have a stream that looks like that is all deep, with nearly straight banks, very wide, but water does not cover the full side of the bed. This is usually a result of a watershed scale instability. What is a watershed scale instability? Meaning that this is a stream that was happily flowing and sustaining life until humans came and started completely covering the watershed with concrete and asphalt, and creating very fast runoff that picks up a lot of pollutant with it, And now for the 1.5 year storm, which is supposed to be what we're seeing right here, maybe, or a little bit higher than that. Now, when you get the 1.5 year storm, the water gets to much higher, and really small storm like a 2 inch or a 3 inch storm, which happens, every 2 to 3 years, will bring the water way above that upper bank. What that does is that the regular flow is actually flowing below the roots of the vegetation, and so you start getting erosion at the bottom because there's no roots in that area where the water flows on a regular basis. You get erosion. It undercuts under the trees, and even though the tree is holding the topsoil very well, it's gonna just fall completely as a tree into the water on a regular basis until uh, uh, either it restabilizes naturally, or a project is done to restabilize that stream. There's also very small erosion problems that can happen. Not everything is due to the whole watershed changing. Sometime, like I'm right here, this picture I took from a bridge, and this stream is not very stable. It's okay. It's not in bad shape, uh, uh, but you can see there was erosion happening right here as a result, and accumulation right here. Why is that? It's because I'm standing on a bridge that had its pole straight into the water, and as a result, it diverted the water flow from where it was going in the center of the stream straight into that bank, which started causing erosion. So sometimes an erosion can be caused by a small local scale uh, trigger, if you want. Another problem that is local scale too, but it can have severe impact, is bridges. When we build bridges, especially if a road is very important, this is in Fort Worth, uh, part of the design that civil engineers have required through the years is to allow for the 100-year flow to go under the bridge, because they don't want the bridge to flood, right, and block the road and prevent cars from driving on them. So they come and build these bridges, and they widen the stream as much as they can, and put these large culvert boxes under the bridge, which is supposed to allow the 100-year flow. But then your stream is so small, it doesn't need all that space. So what's going to happen is it starts depositing your sediments, because the water is flowing, and then it finds this very wide area in front of it, so it's going to spread, and when water spreads, it slows down, and when it slows down, all the sediments in it will settle, and so little by little your culvert starts being blocked. You can see that box is already half blocked, completely blocked to a certain depth. This one is half blocked, so water can only go from this side, and this one is starting to block, meaning that when we're going to get the 100-year storm, it's actually not going to be able to flow under the bridge. Some of it is going to overflow because it's blocking. And we'll address how to resolve this in a couple of minutes. Uh, so channel evolution basically is what happens when a trigger happened to a stream. This is a typical, we call that an E stream. It's a very stable stream where the bankful and the bank are similar. That would be stable. Let's say we start building the watershed. Then what happens is starts widening, and it changes. It's widened right here. This is the plan view. It still meanders, but it's becoming wider. As the construction continues, that channel cannot even handle the water. It starts deepening on the outside of the meander bend, and as a result, all the water now starts flowing here. It resettles this part, and you have a much deeper channel, a G channel. That is badly eroded now. This is where you start seeing soil falling in sheets. If it's still getting more runoff, these sheets starts falling together, and then you have an F channel as a result. And that's the one. That one's going to keep deepening and widening until no more construction is possible. Then with time, sometimes 5, 10, 15 years, it starts resettling slowly and goes from that F back to an E channel. And as a result, you have uh, an E channel that is wider. I don't know if you can see, if you're seeing my part, but and the old bank becomes the upland, and you have a new floodplain existing. This is an example of a C becoming a G. You can see how it's starting to widen slowly. This is an example of a G where we have sheets falling, becoming an F in that part. And this is an F channel that is completely widening, and you can see the water doesn't even cover the full channel as a result. So there are ways to check the erodibility of the bank, and vegetation is one way to do it. This is an index. I'm not going to go through it very fast. You can look it up. It's called the BHI, the Bank Erodibility Hazard Index. Uh, what can we do to fix them? If you want to do a full restoration project, then what you want to do is, this is the old channel red. The first priority, if you have space, if you're in a park, is to recreate the channel based on these three concepts. Recreate the cross section with the bank full and the bank being similar, recreate the meanders, and recreate the channel features on the side of it. This is an example. This is the old stream right here. We recreated a channel with the bank, with the top of the bank similar to the bank full, and the old place can become a wetland, part of the floodplain as a result. The second option is when you're limited with space, you cannot actually create a full separate stream on the side. You recreate the channel exactly where the old channel is. So this is because it meanders, so it actually takes off. You create your new floodplain at the existing bankful now, and then the top of the bank can become your upland area as a result. That's so you're not taking too much space if you're limited in space. And here's an example where this is the channel. The channel is still in the same location, except that instead of having straight edges on our channel, now we created a small floodplain and we have a top bank over here, and we recreated the meanders as a result. Here's another example of it during construction with erosion control blankets, and planting will be done in a later. The last one is the problem when you have a very limited space. The channel is not meandering already because it's in the middle of an urban area, and it's deepening and having a big problem. But because we want to recreate a channel to accommodate only the 1.5 year flow, we do have some space, maybe 5 feet, 4 feet on the edges, to put at least one layer of native vegetation, riparian vegetation. And so that's what we do. And then we can, if the flows are still very fast, we can fix those by using structures in the water. So here's an example. This is a location. This is actually in North Carolina. You have a straight edge on both sides. You have a national forest that you're not allowed to dig into here, and private property on this side that wasn't willing to allow for some space to work. So they created a small floodplain. You can see it here because it's well vegetated, and planted it heavily. And as a result, you have improved control. There's here a structure that to reduce the slope of the channel. You can see why the water is bubbling at this side. So let's talk about these structures that we can use when we're not able to do full meandering. One is the root wad. You take a tree with maybe a third of the trunk and insert it at the meander outer band, and when water comes in, that root wad slows it down and force it to flow in that direction. So this flow is coming in our direction here, and it also helps with habitat a lot. The other structure is what we call a J-hook. So you can see the flow is coming this way. The J-hook points towards it. And what it does is, because of these rocks that are very close to each other, water cannot go in that direction. So it diverts toward the center. These three rocks prevents the water from hitting the next bank and forces the water stay in the middle. And then as a result, the sedimentation happens here, and it rebuilds actually the bank by itself. Here we are looking upstream, so the water is coming towards us, and you can see that's the J-hook at the bankful, and you can see that the water is moving because there are three rocks under the water at that section. A cross vein is basically two J-hooks connected to each other, and you can see here. And one benefit of cross veins is that it can be used as a drop structure. You can restart the slope of the bed from the downstream end. So water is coming in this direction, and then you can start at a lower level here by putting a few rocks underneath the cross vein and starting a new slope. So it can work as a drop structure and diverse water to the center. This is the stream, the new approach for bridges, so that you allow the same amount of water flow through under the bridge without widening. So you do several culverts and you do a mathematical analysis that will guarantee that the flow under the bridge is equivalent to the flow in the upstream part of the river at any depth. And that just takes a little bit of iteration in your flow in the culvert. This is the one here at low flow, and this is at high flow. You can see that culvert is nearly full. These two are less full. As we get the 100-year flow, the water is going to reach here, and the 100-year flow is going to be able to pass under the bridge without flooding the river. But at low flows, only the middle culvert will be operational at that point. Finally, vegetation. We had a lot of talk about this, but these are recommendations for restoration, to salvage on-site vegetation, to do live staking, bare root planting, container plant material, and at the end, permanent seeding. Last slide. If all this is too difficult and you have any impact on your city, make sure that they come up with a no-mow ordinance for a certain depth. 10 to 15 feet would be the ideal. Less is still better, but mowing riparian vegetation is terrible. It reduces the plant that hold the soil in place. It causes erosion. It reduces the water quality treatment of the riparian zones. It actually increases mosquitoes due to water ponding longer times in small depression on the banks as compared to evapotranspiration, taking that up in a couple of days. So if anything, stopping to mow stream banks would be the best solution for you. At the end of restoration projects, the project should be monitored for a couple of years to check that it's working. The morphology are the cross-section pattern and features staying as you built them. Photo documentation helps with that, especially these automatic cameras that take 1 or 2 pictures a day from the same location. You can go back and look at it and notice if there's any change. Survival of the vegetation is an indication of successful restoration. Bank stability, there's no erosion on the bank, is a sign of successful restoration. Shading and temperature of the water, especially if you're targeting a specific type of creature. And finally, fish and invertebrate data is your ultimate test. With that, this is my information, and I will give it back to Kim.
Thank you. My goodness, that was a lot of information. I did like that you ended with no mow, since no mow, I'm a foe of mowing in most places. Thank you so much, Dr. Jabber. That was excellent.